So this problem is asking us to use the method of sections to find the forces in members A, B, and D, E, and we have to indicate if they're tensive or compressive. So we're going to start by just taking the whole system. So we're going to take the whole body, and we're going to draw a free body diagram of it. So when we're drawing our free body diagram, we're not going to take account in the different members. We're just going to draw it as a whole in itself. So this 4 meters like this, up and down, and then it's a total of 8 meters horizontally. And we have this downward force of 12 kilonewtons. And then we're also going to have some reaction forces. So we're going to have our reaction force here, because it's a pin joint, so it's going to go both up and horizontally. So we'll just call this force of F in the Y direction, force of joint F in the X direction. And then we're also going to have an upward force at G. This is just a roller, so it's just an upward. It's not going to move horizontally. So that's force G there. So we're going to want to solve for our different reaction forces. So what we're going to do, we're going to start with the net forces in the X direction, which is equal to force of F in the X direction, and that is going to be equal to 0. So that our reaction force at F in the X direction is just going to be 0. And then in the Y direction, we have this 12 kilonewtons pointing down, so it's going to be negative. And then we have force at F in the Y plus the force at G, and this is going to be equal to 0. So we can't solve for the force of F in the Y direction or G yet, so we're going to have to take the moment, and we're going to take the moment at F because F has the most unknowns. We're going to want to get rid of those. So when we take the moment in the F direction, that's going to be force G times 8 meters because it's moving up. So we're going to take it's going vertically, so we're going to take the horizontal distance, and then we're going to, this is going to be positive because it's going to be going counterclockwise around F, and then it's going to be minus 12 times, and then remember the space from F to the 12 kilonewtons is 4 meters. So that's going to be 12 times 4 meters. And that's negative because this is pushing down. It's going to create a clockwise rotation, and clockwise is negative. And that equals to 0. So then that'll give us force of Fg is equal to 6 kilonewtons. And then once we put it back into this equation, if we put those together, we're going to end up getting that the force at F in the Y direction is also 6 kilonewtons. So then Fg and force at F in the Y direction are equal. So from here, we're going to want to take our cut now. So we're going to do a cut. Since we're looking for the forces in member AB and DE, we're going to want to cut through those, but we're going to want to avoid the joint at C because that's just going to create more force that we're going to have to solve for, and we don't want to have to do that. So we're going to just go down through AB, cut around C, and then back down through DE. So we can draw that. We're going to redraw what that's going to look like. And so that's going to be this. And then we're going to want to incorporate these members still because they're still part of this. Like that. And then we have the force of AC here like this, DC here like that, and then we're going to have forces acting in members AB and DE. And we can label these. This will be AC, this will be DC, this will be AB, and this will be D, E. And then from there, we know that this whole distance again is still 4 meters. And then from the far left side to the first member force is going to be 2 meters, like that. So there we have our distances and our forces that we need to know for, and this is just accounting for this half, the left part of the system. So from there, we can do more equilibrium equations, and that's what we're going to want to do. So we still have this upward force of 6 kilonewtons, because that's force at F in the y direction. So that's still going to be here. We're still going to have to count for that. And so we're going to take our net forces in the x direction, which are going to be dE. We'll do force dE plus force AB, and that's going to be equal to 0, because those are the only forces acting in the x direction, and those are the forces we want and can't find. So we're going to take the moment around D. So D is right here, and we're going to take the moment around D, because it'll solve for the most thing that we want to solve for. So we're going to have 6 kilonewtons of force times 2 meters, and that's going to be negative. It's because it's going clockwise, so it's that clockwise rotation, so that's going to be negative. Plus, we also have force AB, and that's going to be positive, or no, that's also going to be negative, because it's doing the same thing. It's going to create that clockwise rotation around D, and that is 4 meters from D. It's acting horizontally, so we take the vertical distance, and those are the only forces that we need to account for. A and C, force A and C and force D and C are acting through D, and same with DE, so we don't take those into account. So when we have this equation, we can solve for force AB, and that gives us negative 12 kilonewtons, and then it's negative, so that's a compressive force. And then we can plug our force of AB back into that equation, or net force in the x direction, and that's going to give us force DE is equal to positive 12 kilonewtons, and it's positive, so that's tension. And then those are your final answers. Those are the forces acting through members A, B, and D.